everybody. Thanks for coming. For those of you who don't know me, my name is Maiese. I'm the chair of the Manhattan Architecture Department here at NYIT. A couple of brief announcements before I introduce our distinguished guests. First, turn off your cell phones. Second, we are an AIA CES registered provider, so if you haven't already, sign in the sheet where you came into the space, and we can get you some AIA credit for that. Tonight's event is the final lecture in our spring lecture series, and as always, for the entire series and for tonight, I want to thank Jennifer Mitchell, who's the special events coordinator. I don't know, she's probably out of the room right now, but she did a great job again this year. She has done every year for us, so thanks to Jennifer. I'm very happy to be able to introduce Michael Maiese, who's going to talk about curious evolution of glass tonight. Michael Maiese has been working at Bohlin, Cywinski, Jackson for 23 years since he graduated from Rensselaer in 1991. And he's worked on a fantastic array of projects, many of which you know, here in New York City, the Apple stores, also done a ton of university work all over the United States. And I'm not going to go on and on introducing you. I can only say that 5 years of undergraduate education, I had to hear Mike talk about architecture, and I'm happy to hear him talk about it again tonight. So let's welcome him.
Matt is being kind. He did 5 years, I did 6. Is that on? Oh, and it is. How about that? So, yes, I'm Michael Maiese from Bohlin, Cywinski, Jackson, classmate of Matt's. Again, I did the 6-year program. Matt did the 5. A Curious Evolution of Glass is the loose title, but I think it's really a bigger picture of kind of being curious or being inquisitive about what you're trying to do. And we, as a practice, Bohlin, Cywinski, Jackson, take that into a lot of our work. And what my talk tonight will be about is kind of sort of a long evolutionary period of about 20 years of just asking questions of various people and builders and practitioners and colleagues and engineers, and getting always a slightly different answer and seeing where you would take that and what you could do with it. This is the project that I'm going to talk about specifically are going to be a big glass focus, but I thought I'd actually step back and talk a little bit about ourselves. We're five offices. Wilkes-Barre was the first one. That's where Mr. Bohlin's home is. That was the founding office. Philadelphia, and then Pittsburgh. So we have Pennsylvania covered. And then Seattle and San Francisco in that order. We have about 200 people firm-wide. And I've been fortunate in my 20-plus years to actually have worked on projects collaboratively across the practice in all of them for substantial portions of time, not just a few months or things, sometimes years, sometimes 10 years. Little photos of our offices. Similar aesthetic, similar cultural values stretch across them. And it's an interesting matrix if you see the various colleagues that we have through the practice. I have one colleague here today, I think, at least one. Brigham Keener from our Philadelphia/New York office is here. We do, like I said, we practice collaboratively across our offices a lot. And it does help create sort of an embedded culture of exploration. We're probably best known for, in New York, I would think, we're pretty well known for the Apple retail program, various stores. We do academic projects. That's the Caltech Schlinger Laboratory. Corporate projects, that's Pixar. Animation Studios, public, is that's Santa Monica. Not Santa Monica, that's Newport Beach. Cultural, that's the Barn at Falling Water. Hospitality, that's a wine bar in San Francisco. And then retail, that's actually in Shanghai. And then I'm sure everyone here knows those three projects. Again, back to sort of the main topic, or at least sort of my view into the evolution of glass from an interesting seat that I got to be party to in my career. Started with glass early on in, when I first graduated from college, again, a little aftermath. In 91, I started full-time, but I was working at Bohlin, Cywinski, Jackson in 89, 90. Some of you, at least hopefully everyone was born by then. At that time, in the early 90s, glass was, a lot of it was going high performance, coatings, tintings, frittings, and most of the glass technology being given to the architectural industry was based on automotive products being made, because glass production and engineering and research goes for where they sell the most glass, which at that time was the automotive industry. In 97, we started the Rakow Research Library project for the Corning Museum of Glass. Then during my career, subsequently I went from the Rakow Research Library project, worked on the Pixar animation studios, and then a bit on the early Apple stores. The Rakow Research Library is an interesting project because it's an adaptive reuse, and it was a really great client to have, especially if you have an interest in glass, because their subject matter is glass. So when you propose a solution to do something interesting with glass, they're a pretty willing participant and interested to have the conversation. So if you have curious leanings about glass, they not only are willing to actually engage in the discussions with you, they actually can bring some intellectual resources to the discussion. The project had an interesting start. It was a radical adaptation to a 1960s, 50s, 60s building. And in that vintage, it was as you can see, not a terribly nice existing box that thought they were going to expand in both directions. So they did not put a lot of investment in the envelope. So that actually gave us some clues to how you would actually possibly attack this problem. The other interesting problem about the project type is that it was a museum and it's an archival library. And they're also in the floodplain. So it's actually a library that's upside down. The collections are up on the second floor, and the reading rooms are up on the second floor, because in their mission is to preserve, I think this comes right from their website, to preserve all materials and data pertaining to the beginning, evolution, and production of glass throughout time into perpetuity. Something like that. You know, it's a pretty big mission, a little overwhelming. They did, and they were affected by the flood and the Agnes flood, and I'm drawing a blank on the year that was, but so we did have to, you put this sort of sacrificial spaces, which is interesting to say, but the books and materials and paper were the thing that you were looking to save. So you'd put them above the floodplain. Mechanical, office space, all those other back of house functions were down below. So it left us with an interesting challenge. How do you draw people up to the second floor? We were also going into this 1950s building, 60s building, that was not, let's say, the highest value when it was built originally. And by the time we got it 30 years later, it was even less valuable at the time. So we did a simple sort of intervention where the things we added were high value and often glass related. The staircase was brought as a way to, one, talk about their subject matter, and two, bring people up the stairs and take them up. We removed what used to be a terrible ACT ceiling. And behind this glass box, it's a glass, basically, the scheme is a glass box within a box for the archival spaces. Again, with the subject matter of glass and looking at how you would actually execute a glass stair, especially in the mid-90s, sort of the technologies we're using today, the evolution of those technologies is actually pretty stunning compared to where we were about 15 years ago. And the willingness of people to do some of the things now with the inner layers and some of the other technologies that allow us to do those Apple stores and other ambitious glass projects you see throughout have been evolving for various other purposes, but have finally now hit a market where there's an awful lot of it available, and it actually is now competitive. In this circumstance, our goal was to have these glass planks cantilever pass, so you would see the impact of the subject matter. And in this case, it was a simple solution of a wood spacer at the point where you bring the railings past. The planks can be unencumbered, can be in their pure form. We don't have to cope them, cut them, or do any of those things. And you can celebrate a simple glass laminated plank. Leaves us this unencumbered edge and sort of just this pure, simple form, which is all of the objects that we're putting into the sort of renovation of the project were meant to be sort of crisp and taut and modern glass related. The next project, shortly on the heels of that, we were doing the Pixar Animation Studios headquarters in Emeryville. And there was a particular part of the project that was a glass canopy. And at the time, the question was, can you do this in one piece of glass? It's about, if I remember correctly, it's 12 feet wide by 17 feet long, and in 97. That was not one of the sizes of glass that was commercially available. So we came up with a little bit of a workaround, a simple solution of using very simple point fittings to just hold the glass, and then a custom fitting to pick the canopy up. Again, just trying to be as clean and simple as possible. The Rat Cow project and this project is where we actually started working with James O'Callahan of Eckersley O'Callahan. At that time, it was James O'Callahan of Dewhurst McFarlane and Partners. And we also were collaborating with Tim Eliason of Tri-Pyramid Structures. I've had the good fortune of working with both of them for the last 15 years on various projects, both on the Apple side and then some of the other projects that I've had the opportunity to work on. Again, it's just a very simple solution, and in this view, it actually looks like it's one big piece of glass, which was the goal. Now you could actually just buy that piece of glass and do it with 4 points and be done, but in 97, that wasn't really available. The Pixar project led up to the ideas of more ambitious glass, and the Apple stores. This is the first one in Soho. In all glass structure. Subsequent to that, sort of as evolution goes, there's the 2000. This is the 2002 stair, the structural load-bearing stair, all glass-to-glass connections, and then the 2012 version where it's actually a bent stringer out of glass. I still have problems getting structural engineers to give me steel bent stringers. So the fact that we can get structural engineers to give us glass bent stringers is actually quite enjoyable. On occasion, when you have hard discussions with other engineers in various sectors, sometimes you'll show them an image of this and ask them, in a curious way, I think, really, can't we try to give a little more ambition to it? So that brings me to probably the more focused part of the talk is those projects were, and certainly the Apple program is sort of the transparent part of our practice. There's a lot of invisible buildings that we work on, cubes, cylinders, houses. But part of the visible glass or decorative glass version, which has its own interesting evolutions too. Again, the Rat Cow Research Library project. And here's a question I'd like to ask. Does everyone know how you count the surfaces of glass in a window? Does anyone know? Brigham, you better know. Go ahead, Ed.
When you point your finger at the glass and see how often it reflects.
Okay. Not quite as good at the grades that you gave. Yeah, it's true. When I tried that in your class, I don't think I got that one right either, though. So if you're looking at glass, right, insulated units, laminated, or monolithic, you count from the first surface out. So this is kind of fundamental because I'm going to be talking about the different surfaces of glass for the rest of this presentation, so it's kind of a key thing to know. I actually gave this lecture, Brigham, you'll get a kick out of this, in one of our own offices that do a lot of ambitious glass. And at the end of the discussion, someone came and said, "Oh, I didn't really realize you counted from outside in." I'm like, "You've been sitting here for 45 minutes. You just didn't ask." So I've thrown this in. You count from the outside in. First surface is exposed to the outside. Second surface can be exposed to the outside in monolithic in a standard window or laminated skylight, first, second. And usually if this is just 2 layers of, or a single layer of 6 mil, quarter-inch glass, it's 3 and 4. These sandwiches obviously can grow and become more developed depending on how many laminate layers you put in, whether you have triple insulated. There's a lot more complexity and sophistication in it. And the question that comes up that started with this one and continued through all of these projects is, well, the Rakow Research Library is, if you want to treat both sides of the glass, how can you do that? So the question is, when posed in a certain way, if you say, I'd like to frit both sides of the glass, and the immediate answer you get is, well, you can't. Okay. The question is, why? So Frank Grauman, a principal in our Philadelphia office who worked on this project with me, described it this way. Well, you can't frit both sides of the glass because that would be like trying to make a pizza with sauce on both sides. Right? It goes through the oven. So to get the second layer, you can frit the first side, but you have to acid etch or treat the back side in another way. Now, in most clients, and this was in '97, most clients will not typically accept, or most glass manufacturers, fabricators, whatever you want to call them, will not usually warrant something that's exposed in those methodologies. There are now coatings that if you acid etch or sandblast or do these other treatments that you will apply them, but they often will need to be reapplied. Most people are not as interested in taking the risk for a long-term building to have that sort of liability out there hanging on a 120-foot long building, 4 stories tall, 100 stories tall, whatever. But if you ask the question in another way, and you're talking to people who actually make glass for a living and have a lot of intellectual property rights, you can have a discussion about, would you mind if we frit the front and etch the back to do a custom piece of solar shading device? And that's basically what these panels are. We did both empirical and mathematical equations to figure out how we were going to space these lines. And as this diagram is indicating, right, the goal is that the sun can't see into the books, and the people can look through the windows out to the view. Pretty simple partie. Except we wanted it to be progressive, and we also wanted to see the sky. So we calculated the panels. We did both mathematical testing, and then we actually built 12 by 12s in our own office with tape, because we're clever, paint and tape. It was a big weekend at the office, trust me. And you hold them up, and then you're walking around, and you have sun, and then you put lights on them, and you try all these interesting things. Sometimes late into the evening, which then leads you to other interesting thoughts. But once we thought we got it right, and we did those mathematical equations, and we had a very long string of decimal points of figuring out how exact we were going to make these, and we have this big mathematical equation. We had 3 of them made, actually, and had them installed exactly where to mock it up, to truly mock it up. Because if you're going to do something with glass, what I've truly learned, if you're going to do something with glass, having full-size mock-ups, at least a swath of it, is critical, because you can never really predict exactly how that glass is going to perform. Just the color in different regular anneal glasses and the color difference in low iron glasses is stunning if you put big pieces of them next to each other. So it did not work the first time. They could not fabricate the panels to the tight tolerances that we were exacting from them, because when you do a 12-foot stencil on a 12-foot piece of glass that's 6 feet tall, and you pull it on both ends, the fabric stretches, so then it waves. So then the lines don't align, and it's also not repeated on each one. So two things we learned. One, that was a problem that we didn't anticipate at all. And two, we needed to give a little more breathing room tolerance for the lines and get them to overlap. And our exact perfect application in real life needed to have more tolerance built into it for both fabrication, installation, and just human nature. So this is a much younger version of myself and colleague Steve Chato, principal in San Francisco. We're basically using the glass as a shop drawing where we want the new lines on it and saying, hey, can you make one of these? So they did. And then we went out, put this on the back of a truck, and drove around in Calgary in April, which is like going to find winter and praying for the sun. And it did actually work. You get this moving, this simulates the original. This one is the A panel, and this is the B panel. We also then looked at the various math and equations and worked to figure out what is the optimum line spacing, because that shadow, as you saw in this image, will not cover the entire 5-foot window throughout the whole day. But you figure out what is its maximum shading, and you live with the margin of sun that comes through it. And we then looked at, well, the other impact of the screen wall is actually backlighting at night, so it becomes a lantern in the landscape. So we basically optimized the angles based on where we would set the lights and work those math equations back and forth until we hit what we thought was a pretty good compromise. Again, this is a top panel, and then these two panels are identical. So this is, if I remember correctly, this is the A, and these are the two Bs. The sun, generally, it shades out somewhere, I think it's like 80+% of all the daylight onto this window, which also has a high-performance coating and a UV inhibitor inner layer to really make sure that the UV does not see the books. Preservation of, again, the paper about the glass is the mission of the thing. But the views up, and it gives us the views up to the sky. And this is, again, where we started working with Tripyramid on our custom fittings. And at night, this is the reading room and the lantern. And at some day, I believe that will eventually become park, as opposed to parking. The next sort of project related to glass, and this one's a little more straightforward and simple, but is actually our alma mater, Rensselaer, the Biotechnology Center. It's a 260,000 square foot, 220,000 square foot science and technology building, primarily wet biology labs with a lot of office space. It's fundamentally a 3-building partie. There's the sort of the historic facade of office spaces that run down 15th Street. There's the modern part that turns into the quad, and then there's an enormous machine for research behind. And the skylight is sort of the bridge, natural outdoor street between. And the real objective was to be able to create this space, keep it naturally ventilated so we didn't have to invest in air conditioning, and give people in upstate New York, the students, which a nice indoor space for many of the months where it's not so nice to be outdoors. To achieve this, we invested in, this is a VE52M product from Viricon. It's a Ford blue, highly engineered, older technology blue glass with a 2M coating, which at that point was their best performing low E coating with minimal reflectance. And then we actually added 3 different densities of frit pattern to it. And in this case, it's that story again. Where are you putting the frit? In this case, you put it on the second surface inboard of the light. And then the bottom pieces of glass are laminated together for safety because it's a skylight. That gave us the coverages we needed that allowed the CFD analysis model to show that we could naturally ventilate the atrium space and not have to provide any air conditioning and simply do it by inducing draft with the smoke evac system that was in there, thereby saving the entire cost of investing in an air conditioning for, what do I remember? It was about 45,000 square feet of space. It's the sort of three planes, and they come together in this interesting knuckle space. And again, it's three buildings moving separately, and New York is actually a seismic zone. So this corner is an interesting kind of Virendale truss on its side, and will bend and sway, and it's actually attached to the smaller building and just rides against the top building with sort of a slip fitting. The real item we were struggling with in trying to figure out the aesthetic of this was actually figuring out how you can get a consistent look even though you have 60, 40, 30%. And we did that varying those two little lines between the reoccurring larger 5/8" line. We think they actually provided two benefits. One, it gave us a constant kind of view from inside the space, and more importantly, also at night, it gave us a sort of a reflecting to bounce the light down, because we were basically bouncing the light off the skylight back into the space at a low level. The final sort of case study is actually this decorative glass project for a corporate client out in Southern California for Creative Campus. It is it's a 7-acre site, part of a larger campus. 7 acres, there's a parking garage and a building with amenity spaces in it and some existing buildings on campus, and this was our whole site. And the mission of the glass in this case was less performance-based from a solar thing, but actually as a unifying factor, sort of wayfinding and campus building. So we have these 5 different points of sort of intervention of the glass and decorative glass in this case. And we had a concept of a gradient, color gradient that starts at blue and ends up to yellow to white. And we looked at different technologies that were available to us. There's various ones. There's direct print to glass. There's printing on PETs. There's printing on PVBs. And there's a few other ones that, in all honesty, I can't remember. But and I will ask them, and then someone will say something, and I'm like, well, that's not what the other rep who's selling me the same product said. But anyway, it's an emerging technology, and we looked at all of them, and we started off with a color scheme and trying to determine both color gradient and density of color gradient, because that's actually a variable. And what I find in this technology at the moment, it is certainly getting better, but if you try to print your document from your home computer and then try to print it at school, print it at a friend's house, it doesn't always come out looking the same, especially if it's a full bleed color graphic. The same would be true with these giant printers that they're using for any of these technologies. So our investigation started with watercolors. We had samples made. We made digital files, so we created the custom artwork in Illustrator for the project at full scale, which is 7 stories. And then we ordered panels from 3 different vendors, 4 different technologies, and as you can see, none of them matched. They all get the same digital file. And so that made us wonder, what's that about? It's a good question. And then you would ask them, so this one in the case in the middle actually is a custom frit first surface, doing a custom graphic as one exploration. But all of these things, we had 125, 150 samples. And there couldn't have been more than 6 that matched each other. And those were in pairs of 2, not pairs of 4, because, again, we ordered 5 of each set. Interesting. So we looked at them daylight. We looked at them at night. We looked at them backlighting. These explorations are a bit into the color, the line thickness, which type of first surface treatment you're getting, whether you're doing acid etching, sandblasting, etch frit, and true custom acid etching, which is only available outside of North America. There we go. So back to the watercolors and the constant gradient. The gradient basically starts, and it's because it wasn't complex enough to do it with watercolors, we thought, since we have 6 surfaces to work with in our general palette, we thought we'd at least use 2 of them to make 2 different color gradients based on the same pattern, but accelerate the color gradients past each other so that we'd get more richness and variation. It's actually much easier for me to say, which I obviously did not do very well, and it's even harder to pull off. We looked at these line spaces and trying to figure out how dense do you want the line work and how do you space that? And then we also had this other interesting circumstance come up is we started layering cost into this and panels of glass and layers of glass, so then not all pieces of the glass on the project were going to have the same layers. The primary one we did is 3 layers of glass. It was 19 mil, 6 mil, 6 mil. We have other ones that were just 6 mil, 6 mil. We have ones that were 12 mil, 6 mil. How you combine these different color gradients when you compress them, and then there's this interesting debate about if you have these 2 different lines, and what we were staggering them because we learned at the Rakow project that you need to have an overlap of them when you put it through because the refraction in the glass will play, and the way your eye closes the gap when looking at it, you need to actually overlap them so you can get either the closure or the openness you're trying to achieve. We did settle, I'll jump back for a second, we did settle on the thinner line work. We looked at the larger ones. These are much closer to the scale, the ones at Rakow and at Rensselaer. But this pattern is the one we actually believe gave us the maximum color from afar, but the minimum blockage when looking through it when you are up close. And we tested that a lot, both. Again, you have to test it at full scale. And then we realized that you do need to engage a fabricator and start syncing your software and your color gradients to their technology. And that's where we started. This is us looking at them full scale height, printed out, and trying to match. And these are 12 by 12 panels. It was a pretty large collection of glass, decorative glass. There were 5 distinct elements. There were 2 sides to most of the elements, and some of them had 3. And this is sort of just tracking each of them, because each of these panels across here get a custom artwork. And these panels, these are for the parking garage. There's actually 132 of them. And there's 4 different gradients, but they scale around. So we started then also making shop drawings for them and looking at the different layers and the colors, and then some of them are opaque, some of them are acid etched on the first surface, again trying to create these different densities or use them as either blinders or different visual cue devices. The parking garage is a very straightforward structure, but the goal is to give it a lot more life and make it an element when you're coming in off the freeway so that you can see it and you kind of know your destination point. The explorations into detail line work. And then the shop drawing process comes in and you start trying to account the 12 by 12s, and this represents a 10-foot panel, the bottom 6 inch or the bottom 5 inches of it in blue, and this is what the top 5 inches would be, and then our goal is to align it so it's a constant gradient all the way up through the panels. Full-size mock-ups, testing them and looking for the various abnormalities that show up in sort of this large-scale printing process. And we had a few that showed up. We were testing the color gradient versus a collection of baselines. And then we put them on the side, and that's the panels for the main stair. Seeing if it goes from blue to green to. There's our control samples. This is our mock-up. The first one did not actually appear as blue. Again, getting full-scale mock-ups is important if you're trying to determine how blue something looks in what is otherwise a fundamentally green substrate of natural glass. The panels were pretty successful. They do work as these wayfinding devices, and when you're on the campus, you can actually kind of find your way around towards the major vertical circulation points of which is otherwise a 7-acre site. This is one of the entry pylons. It is actually opaque. That was one of the color patterns that I showed in there that we actually filled in the back line in the B layer. This pattern is identical to the one on the left. The one on the left, let's see. As you can see up to the mountains, the one that I was showing you on the right is actually acid etched so that you cannot look down into the loading dock. So this is the acid etched side, and this is the more transparent side. Looks up to the mountains. The main stair, again, you want to be able to see through, but from afar you'd like to have as much color impact as you could. That was the balancing act we were working for. The main stair on 7 stories on the end of a very long concrete frame building in a seismic zone also was a little bit of a challenge from a structural engineering standpoint. And we were fortunate to work with Tri-Pyramid, supplied some amazingly nice fittings that both take up that seismic restraint, because if you put large panels that weigh about as much of a Volkswagen hung off the end of a 350-story building, there's about 3 inches of movement. And of course, to make it simpler, we also shingled the panels. So there's this interesting challenge of front and back, side to side, up and down movement that needs to be accommodated into what we affectionately called the boomerang. These fittings are really interesting industrial design pieces. Again, the garage piece with its varying, very subtle layers of green. Both panels are acid etched, so they actually at night they actually glow. This is another sort of exploration that I've been fortunate to be part of. Starting into is the Frick Environmental Center that we're doing out of the Pittsburgh office. It's going to be LEED Platinum. Its mission is education. It's for the Pittsburgh Conservancy, and it's their environmental teaching center, basically, at Frick Park, historic Frick Park. And part of it, the project, it's also a living building challenge project. We're hoping to achieve that rating after it's completed. One of the components of that is sort of teaching and learning process. And actually in our building for energy consumption, we're actually using phase change materials. And we're working with Dale Clifford, Biologic Design Group, who is also a professor at Carnegie Mellon in Pittsburgh, to develop these phase change material sort of demonstration tiles to try to educate people to the idea of captured energy. It's a project that we've just started, but I think it's going to be pretty interesting and pretty promising of where that could go in the future, sort of using phase change materials, besides doing them in sheets in the ways that they do, and there's people doing other biomorphic sort of products. I think the idea of being able to celebrate them within a facade is actually a pretty interesting thing. So thanks. Any questions?
How do you factor in cleaning the glass as you're designing these structures?
How do we factor in cleaning the glass? It is always a consideration. Depends on the larger buildings, right? Have dunnage that drops over the sides. Many of the smaller projects, 2 and 3 stories, you can get from a boom lift. The atrium has a special inside boom lift that with this outrigger arm that we actually had to find a place to park in the atrium space so they can go up and actually they didn't ask how to clean the glass. They asked us how do we change the light bulbs. But you know, same sort of thing, right? I mean, it is an issue. We live in these buildings, right? And you have to be able to maintain them. That's important. And the ones that are maintained are usually the ones that also people like or love. You know, those are the historic buildings that have the longest permanence and have a real memory with people. So it's important to be able to, one, make great buildings, but also have them, you know, become fond to their owners so that they are treated well, because it's a serious endeavor.
What are the costs of these projects just for the glass? Because I assume this last project, the
Creative Campus.
Creative Campus and the Apple Store are immensely expensive. Is it right that one glass panel at the Apple Store is like 300,000 each?
Maybe. The glass per square foot question, right, is a general question. The larger, it's an interesting set of economies of scale. For the Creative Campus project, the decorative glass, certainly, glass comes in one, size, weight, and how many times you treat it, whether you flip it overside and do something to it or whatever. All of those things do have a cost to it, and it's sometimes a multiplier effect. If you have large pieces of glass, you get into this interesting question of how many man hours it takes to actually install one. But if you have a bunch of small pieces of glass and you're using the same crew. So there are certain economy and breakpoints that commercial glass versus giant monumental glass, you know, there are breakpoints that you try to work within. The Rathkow Library project, the goal was to push it right up to what you could do economically with a 3-person boom lift and put them in and fit them with only 4 points, right? You get into these sort of discussions about, well, what is the more economical version? Would it be better to have a bunch of smaller pieces and more fittings? Is it better to have, and that was actually somewhat of a teamed with both the designers and the builders working to figure out what is that sort of sweet spot of repeating component. The economies come if you do a bunch of the same pieces, whether they're really big or really small. Obviously, the more production you can get out of the repeating pieces is where the value is. The envelope of that whole building, 330,000 square foot, they actually erected it in 24 working days because it was unitized, and they were big pieces of glass, and they had big cranes and just fly it. You know, it's similar to what they do here, right, in New York. Vertical time is money. People time is money. So sometimes big pieces or more unitized or stacking more of them together is actually somewhat economically feasible.
In the Pittsburgh project, did you work with any of the Pittsburgh companies? I know there's a lot of glass history in Pittsburgh. They have a lot of the PPG, and they're famous for the glass bricks. They're one of the biggest.
You mean for the Frick project?
For the the last project you showed, the one in
Frick
Pittsburgh.
project. It's actually out to bid right now.
Mm-hmm.
But yeah, we have been, and it is an installation project in a nonprofit building. So you can imagine we've asked as many people as we could about helping to donate product and material. That rendering we show is actually kind of one of our own internal marketing tools, and we've created a modular system to test these. Because there's a bunch of empirical knowledge we hope to actually acquire by making the panels, and if one side of the glass is blue, the other one's high performance, are we going to be able to do it? I'm curious to see if we can do it out of Gorilla Glass, if I can get anyone to give me a bunch of 9x9 Gorilla Glass pieces. Dale Clifford actually makes these mock-ups himself, and then he helps on the production side. So yeah, we are trying to leverage the historic glass-making industry in Pittsburgh and Corning and any of these other people that we know because they've printed big glass jobs for us in the past. We're calling them samples when we ask them.
Could you talk a little bit about what the sort of state
State of the art?
Yeah, and also like what you're most excited about for the future of glass, for the next
Sure.
50 years or something like that. I don't know.
Okay. State of the art. Wow. I actually find the print to glass technology, I think there's an awful lot of promise in that, just from a very commercial standpoint. The ability to actually print, take a piece of glass and print two different colors on it so that the sun sees a white and you see whatever you want inside is actually, I think, pretty appealing just for a performance standpoint. And that's pretty simple. What is also interesting, though, is the monolithic glass, as you know by many of these large projects being done in New York, which is helping to push the envelope. There are really big pieces of glass being made now. The single largest, as I know to date, the single largest printed glass machinery will do a 12-foot panel by, I think it's 8 feet wide. So those machines aren't keeping pace with the autoclaves and the production. And the interesting thing about glass, going back to the Pixar Canopy, when the question was asked, why can't I have a 17-foot by 9-foot piece of glass? Well, at the time, they were only making 144 by 204, so that's an inches panels of glass commercially. But if you've ever gone to a glass plant, and I suggest that you do, or at least go to the Corning Museum of Glass, because they have a great exhibit of how glass is actually made. But glass comes out on a continuous ribbon. They never shut the machines down. They rebuild their furnaces every 6 years, and it takes them, I think they try to do it in 94 days or something. It's something just insane, right? It's this giant, hulking machine that looks like it's from, the Egyptian period. It's stunning. It is an old soda lime and ash falls in, it comes through, it burns, and it's this continuous ribbon of glass. So fundamentally, the width of the machine is your limit in one direction, but if you could figure out a way to take it all off as it comes off the assembly line, you could have an infinite piece of glass, obviously until it breaks. But the catch is you don't have any machines that can do anything with it then, right? That's the limitations on glass fundamentally are down to autoclaves, printer, cutter machines, things like that actually change the glass. The phase change materials, these other questions, and the other thing people are looking at things into these fusion glass technologies, which is basically the cover of all of our phones, right? Your iPads, your TV screens, right? Fusion glass, which was made by Corning. Wow, they've had that patent for a while. It's really thin, really strong, right? But it has no rigidity to it. So then you laminate it with other things, and there's a bunch of, you can imagine a bunch of opportunities of being able to print on it, make safety glass, make thin, lightweight safety glass that also gives you hurricane when you put those with the inner layers, and bulletproof, and there's a lot of those opportunities. The later generations that are coming out with coatings also need to play into the mix, right? Because we need to basically, what you want, the perfect thing is you want the perfect clear glass box or glass window that also allows in absolutely no solar gain, right? Which, that's virtually impossible. But there are now, we're into triple silvers, which is Solar Band 70, and now there's actually 4 layers of silvers deposited. But I'm curious in all these new engineered materials that you may be able to bond in with the glass that actually give it some life. And how does that smart glass, there's active and passive state shading now. You can buy view windows, make one, you can dial up to 20% to 60%. And there's also passive versions when the inner layer gets heated, it actually darkens itself. It's kind of like it's like the eyeglass technology, right? So I could go on forever, but someone may have another question.
Was there a reason why you went with the narrow stripes as opposed to the wide stripes for that building? Is it other than aesthetics?
No, it was actually, it was actually visual impact of wanting to be able to see the maximum out of it and get the, you wanted to have it's odd because it is the same aperture mathematically and the same, 4 inches of stuff between the stripes, but your eye stitches together the thinner stripes better. It just fills in the rest of the equation. I mean, you know, you go to LaGuardia, right, and you see the half inch white, clear half-inch, you know, it's like, which is why the biotech one has the different layers. That very standard one, I find just a little underwhelming. There's the other pattern that was all the rage, and all of the major manufacturers cover it. It's the 1/8 inch line, 1/8 inch clear, 1/8 inch line. And I don't know if you've ever walked up to that, but that moire pattern makes me nauseous. I can't, you know, it's just either direction, this way or this way. I personally am a fan of the horizontal lines. I don't like the vertical lines, but that's just personal choice from being able to have several large mock-ups made over the last 20 years.
I know you said the last project that you did was platinum LEED certified.
Will be.
Will be.
Yeah, it needs to be built yet.
Are there any?
But that one, this one's platinum LEED.
Oh, okay.
That one? Yeah, platinum LEED.
Do you come across any like major environmental implications across the glass facade systems?
Major environmental implications. Tell you what, how about I'll take another run at it. In some ways, the LEED system is important because it helps put a metric and creates a greater ambition, especially for people that are the buying public, or the people that empower us as design professionals to go on a mission of trying to also do good design that is frugal in both first cost and resources, right, which is operating cost. In our private and public sector work, we're fortunate we are not, we are usually given a mandate of create some sort of LEED level, right? They say that, you should do that. But we find just good design is the right way to go. Being cost conscious, both, again, first cost and energy costs, because in the real cost, especially in those research buildings, which is a large portion of our practice, large academic research buildings consume more energy per year than all of the other types fundamentally combined. It's due to the life safety issues related to one-pass air for fume hoods and the lighting requirements so that laboratories are safe, and then their duration of use is very long. You know, the people in labs are silly, just like architects spend all night in their labs, and the lights are always on and they're always occupied. So just doing the right sort of design, and the big thing about that is simply to right size your system so they're operating at the right efficiency. You have to actively go after those important things. And we have a process in our office. I can't believe I'm going to go to this. Parallel process programming. Yeah, I know, it's awful to say. That you bring all the stakeholders in. We do these large charrettes early to talk about building systems, intent of building, design, all of it, MEP, mechanical, the owners, the operators. And we have sessions about how will you best maintain this so it gives you the best functioning facility. We do that a lot, and again, it's something that certainly became derived out of our working with university clients who keep their buildings for 100 years and they don't have any operating budget. So, does that touch on any of the questions that you had in mind?
Yeah, God, I was going back to the cooling system that you mentioned in that building. Was that
Which cooling system?
the one that was able to cool, I don't know, the whole building?
Oh, yeah. So I'll touch on both of them then. The research laboratory, right? The environmental savings on that were threefold. One, the laboratory bar in the 3-building partie is its own entity. It's its own captured volume, so that we only had to condition that level of air with one-pass air, so you're not paying for all the air that comes in and you have to then exhaust out the roof, right? So you then sequester that from the office spaces, because office spaces you can use recirculating air, so you don't have to pay, especially in our East Coast environment when you have to pre-warm the air typically, and then in our summers, of course, we have to pre-cool. You don't have to do those because you're actually being able to do that with your recirculating air in the offices. So actually, it's just good design if you can separate those sorts of two separate uses so that you can maximize the typology of the system that you're using for that building component need. That's the best way to go about it. The atrium itself has no air conditioning at all. It's completely passive. It gets borrowed air from the offices. So if the doors are shut and it needs some vent, we turn the smoke exhaust in, and it will induce a draft that will open up louvers on the outside of it, and will pull air across the ceilings of the offices, giving them a bit of a chilled beam effect before chilled beams were actually in play, and actually bring in air that at most time in upstate New York, you know, the design temperature of air is, I believe, 49 degrees or something. I don't know. Anyway, that's how you do it. We just eliminated the system by using either the recirc air from the offices or bringing in cool outside air, because it's a hallway. It's a really nice hallway, but it's still a hallway, and you can let those temperatures fluctuate more, and that's how you're able to really create long-term savings. Bueller, Bueller, Bueller.
All right, well, I'd like to invite everybody to go outside and have some drinks, some food, and thanks again, Mike.
Thanks.